And the implications are very important. And some of you will be involved in your careers in the communication industry, either as engineers or business leaders or government leaders. And you'll see why, in the next few minutes, why this is such an important concept. And the basic issue is how fast can we send information? Or you can use the word data if you want instead of information. And we're going to send information from A to B, and what's the data rate? I don't mean the fact that the data travels at the speed of light. I mean, what's the data rate? For example, how many bits per second can I send from here, front of the room to the back? So it could be a cell phone, it could be a radio station, it could be wireless internet, it could be anything like that. We're trying to send information from one point to another. And that's gonna, we know that's important how fast we send information. We said last time, we used the model of an AM radio as the model. And AM radio, we said, worked like the following. Actually, I have a few of the handouts. Anybody not here? Let's see, I'll send these around. These are the handouts from Friday. If you didn't get it on Friday, there's a few of them. We said an AM radio, it works like the following. If we're at AM station 1000, that means there's something at 1,000 kilohertz. There's a sine wave we call the carrier. And so that just goes up and down. This is the V carrier, the function of time, goes up and down at 1,000 hertz. And the information we're trying to send, for example, on AM radio is sound. So we have some audio that might be some wave like this that goes up and down in amplitude. And I just use here, for example, let's use the frequency of the sound equals to 1 kilohertz, which is 1,000 hertz. So this would be, well, this wouldn't be music or voice. This is just one frequency, but we're going to do it for one frequency, and then we'll generalize. And what we said last time was what an AM radio station does. What an AM radio station does is the following. It adds an offset to the audio. This adds an offset so the signal is always positive. So this is some multiple function time. And then it multiplies the carrier. So it takes the signal here, multiplies it by V carrier as a function of time. So we're multiplying some positive number between 0 and some positive value times that high frequency sine wave, and we'll get a high frequency sine wave whose amplitude goes up and down like this signal. So there's no physics or anything in this yet. We have some kind of circuit in the transmitter that knows how to multiply the audio you're trying to send. Well, it adds an offset, and it multiplies that high frequency signal times the audio, which is much lower frequency, and you get something like this. And this voltage here, let me just say, this idea of, if you look at this, what we're really doing is taking that high frequency wave and just changing its amplitude. So the amplitude is big, the amplitude is small, the amplitude is big again. So we call this idea amplitude modulation. Modulation just means change. So we're changing the amplitude of that carrier frequency. We're changing the amplitude of the carrier frequency. And this thing goes up and down. Then we take this signal here and we send it to the antenna. So here's the ground. And we have an antenna here on the top. So we take this voltage, which is, let's call this VAM here, our amplitude modulated signal. We'll take VAM and we'll take that voltage, we'll put one end up high and the other end down low here. And this is the antenna. And as this voltage goes up and down, the electric field will point this way, or the electric field will point that way, depending on what that sign is. So this electric field here alternates. Goes up and down and up and down. So this represents here the antenna at the radio station. And the electric field goes up and down, and that creates this electromagnetic wave that we discussed on Wednesday. So the electromagnetic wave goes down. And over at the other end, we have two wires, and when the electric field at the other end goes up and down, that creates a voltage. So we put a voltmeter here. We have a voltmeter here that measures what's coming out, what's coming in, and that goes to our receiver circuit, meaning the listener. Receiver. So this wave is over here. And that's an antenna. That's a bit of a block diagram. Questions so far? So the signal that we get at the receiver, looks just like the one we sent out, but it's smaller. And so what we so V at the receiver has some amplitude, and it's got sine omega carrier t, where this is 2 pi times 1,000 kilohertz, times sine omega audio, that, for example, was 1 kilohertz time. And you may remember that sine A, sine B is equal to 1/2 cosine A plus B minus 1/2 cosine A minus B. So this thing is V amp cosine omega C minus omega audio T minus V amp over 2 cosine omega carrier plus omega audio times T. So this would be 1,001 kilohertz, and that would be 999, and that would be 1,001. So just to digress, suppose I was listening at the receiver, I listened to that, let's just say, if I just listen to a perfect sine wave at the receiver, am I able to write down that some information is coming in as a function of time? If all I said is, you see this signal, could you write down versus time bits or tell me what the speech is or anything that represents some kind of information? You just hear a constant sine wave. You know, one of those test signals. That's all you heard forever. Could you write down 0, 1, 1, 0, 1, 0 coming in, or write down the speech you just heard, or no, right? If all you heard was this, there's no information. There's nothing useful being transmitted to the other end. Now, if it turned on and off, then there's something, you know, something's going on. Maybe you could say it's on, it's off, it's on, it's off. But if all you heard was a sine wave, you wouldn't be able to see anything. So, let me just right here. If I were to write plot a frequency, if I were to plot frequency, coming in, here's frequency axis. And here I had my, this little arrow that represented, that was my carrier. And after I modulated it, I had a signal at 2001, and I had another signal down here at 999 kilohertz. So I was something here, and this is my original signals at 1,000 kilohertz. So speech, obviously I'm talking, and you could write down my words. So there's some information in some abstract sense being transmitted. What's the difference between my speech and a constant sine wave? First, there's a lot of frequencies in my speech, right? And they're not all of constant amplitude. Sometimes I stop speaking and they all go away. So my speech is composed of many frequencies. And because it's composed of many frequencies, I can, well, you hear music, you hear speech, it starts and it stops. There's some information being transmitted. So that means, let's say the speech goes, let's just say roughly, might be from 100 hertz maybe to 5 kilohertz. So that would mean the wave that's going out is a superposition of all of those different waves. And then if I take therefore, then when I take I multiply the carrier wave by a low frequency wave, 100 hertz wave, I'll get a signal at 999.9, and I'll get another signal here at 1,000.1. And when I multiply by 5 kilohertz, then we get a signal out here at 1,005, and I'll get another sine wave that's going out at 995. And I'll get all different sine waves, for all those different frequencies. I'll have some kind of signal going out, which is what my lines mean. I'll have some kind of signals going out at all different frequencies. So maybe from here to here, and then all the way up to here, there's some kind of sine waves going on. Let's see. By now, all of you have had a math course. probably all you had a math course doing frequency content or Fourier analysis, where you have a periodic signal, and you say what kind of frequencies are in there. So vaguely familiar. That's just exactly the same thing. We're looking at some kind of waveform, we're breaking it down to what frequencies are in it. And speech qualitatively, you know it's got high and low frequencies or whatever. So what this says is, when I'm talking, the signal goes out over the AM radio as frequent as waves in it at all different frequencies from 995 to 1005 kilohertz. That's what's out there. And how much wave there is at each frequency depends on what I'm saying at a given time and the frequencies in my voice at any given time. So to send information, that requires multiple frequencies. So the electromagnetic wave in this case is a superposition of waves from 995 to 1005.